How does raw iron transform into the steel that builds skyscrapers, bridges, and machines? Let's discover the powerful, fiery world of modern steel manufacturing. The plate bending process begins with the preparation and positioning of a large steel plate that will be formed into the required curved shape. Due to its considerable size, thickness, and weight, the steel plate cannot be handled manually. Instead, an overhead crane installed in the workshop is used to lift the plate safely from the storage area. Steel lifting slings or chains are securely attached to the plate, ensuring balanced lifting and preventing unwanted movement during hoisting. Once the crane operator lifts the steel plate, workers standing on the shop floor carefully guide it using hand signals and guiding tools. Their role is essential to keep the plate stable and properly aligned while it is suspended in the air. The plate is slowly moved toward the plate bending machine, maintaining a controlled speed to ensure safety and accuracy. Throughout this step, clear communication between the crane operator and ground workers is maintained to avoid misalignment or sudden movements. As the steel plate approaches the machine, workers gradually lower it into position. The plate bending machine typically consists of multiple heavy-duty rollers designed to handle thick steel plates, such as 56 mm plates shown in the process. The plate is carefully placed onto the lower rollers of the machine. Workers make fine adjustments to ensure the plate is centered and aligned correctly with the bending axis. Proper alignment at this stage is critical, as it directly affects the uniformity and accuracy of the final bend. After positioning, the machine operator begins the bending operation by adjusting the upper roller. This roller applies downward pressure onto the steel plate, while the lower rollers rotate, pulling the plate through the machine. As the plate moves forward, it is gradually bent into a curved form. Instead of bending the plate all at once, the machine applies pressure progressively. This controlled approach helps prevent cracking, surface damage, or uneven deformation, especially when working with thick steel. During the bending process, the steel plate passes through the rollers multiple times. After each pass, the operator slightly increases the pressure or adjusts the roller position to achieve the desired curvature. Workers closely monitor the plate's shape, checking the bend radius and overall geometry. If necessary, the plate is repositioned or rotated to ensure consistent bending across its entire length. In some cases, partial bending is performed first, followed by additional passes through the machine. This step-by-step method allows greater precision and reduces internal stress within the metal. The rotation of the rollers and the gradual application of force ensure that the plate bends smoothly without sudden deformation. Throughout the process, the machine operates at a controlled speed to maintain accuracy and safety. As the plate reaches the required curvature, the operator reduces the pressure on the rollers. The machine slows down, and the plate is carefully guided out of the bending area. Workers assist in supporting the plate as it exits the rollers, ensuring it does not drop or shift unexpectedly. The curved steel plate is then inspected visually and, if required, measured to confirm that it meets the specified bending radius and dimensional requirements. If the curvature is not yet perfect, the plate may be fed back into the bending machine for further adjustment. Minor corrections are made by fine-tuning the roller pressure and repeating the bending cycle. This iterative process continues until the desired shape is achieved with high accuracy. Once the bending operation is complete, the overhead crane is used again to lift the finished curved plate from the machine. Workers attach the lifting equipment and guide the plate as it is raised. The plate is then moved to a designated area for further processing, such as welding, assembly, or surface treatment. Overall, the plate bending process relies on the combination of heavy machinery, precise control, and skilled human coordination. The use of an overhead crane ensures safe handling of large steel plates, while the plate bending machine provides the controlled force needed to form thick metal accurately. Each step, from lifting and positioning to gradual bending and final inspection, plays a crucial role in producing high-quality curved steel components for industrial applications. The process of cutting an H-beam steel bar using a cutting torch begins with careful preparation. First, the H-beam is placed securely on supports to prevent movement during cutting. The operator measures and marks the exact cutting line to ensure accuracy. Next, the cutting torch equipment is prepared and connected to the gas supply. After checking safety conditions, the torch is ignited and adjusted to obtain a stable, high-temperature flame. The flame is directed along the marked line, gradually heating the steel until it reaches cutting temperature. Oxygen is then applied to create a clean cut through the thick section of the H-beam. Finally, the cut surface is inspected and cleaned to remove slag and sharp edges. The video introduces the CTBH-8 profile and tube bending machine, a powerful calandra designed for shaping large tubes and structural profiles with high precision and efficiency. This machine is specially engineered to bend tubes with diameters of up to 8 inches, making it ideal for heavy industrial applications and metal fabrication workshops. Equipped with dedicated tools for tubes up to 8 inches, the CTBH also processes flat bars up to 5/8 inch thick and 4 inches wide, including flange sections. In addition, it features tooling systems for various structural profiles such as U, I, and H beams, as well as angle bars. The machine can also bend solid round bars and square bars, offering remarkable versatility for different production needs. With a 10 horsepower motor, the CTBH-8 delivers strong and stable performance during bending operations. Its electro-hydraulic control system ensures smooth, accurate movement and reliable pressure control throughout the process. The machine can be operated either through a control panel or by foot pedal, providing flexibility, convenience, and improved operator safety in demanding industrial environments. The Cosamac 3.75 edging machine is designed to bend flanges on metal sheets up to 3.75 millimeters thick with precision and stability. The operation begins by drilling a 16 millimeters hole at the center of the workpiece. After that, the central fixing screw is removed, and the sheet is positioned and secured firmly using the screw to ensure proper alignment during rotation. Next, the distance between the rollers is adjusted according to the desired flange height. In this example, a 10 mm setting is selected to reach the pulley limit. Once the adjustment is completed, the head motor is switched on to start the rotation process. The operator then tightens the spindle gradually, applying approximately half a turn of the spindle for each full rotation of the sheet. As the rollers press firmly against each other, they begin forming the edge at a 45-degree angle. When this angle is achieved, the lifting motor is activated. The head is raised smoothly until the required inclination is obtained, completing the bending process. At the end of the operation, the spindle is loosened and the head is returned to its original position, preparing the machine for the next workpiece. The video shows the process of bending square steel tubes using a box steel bending machine. First, the operator measures and marks the required bending position on the steel tube to ensure accuracy. The steel box section is then placed between the machine's rollers. After adjusting the pressure and setting the bending radius, the machine is activated. The rollers rotate smoothly, gradually applying force to the steel tube. Instead of bending it suddenly, the machine shapes the material step by step to prevent cracks or deformation. The operator carefully monitors the alignment and repeats the rolling process until the desired curve is achieved. Finally, the finished bent steel box is removed, ready for fabrication or construction use. This video demonstrates the operation of the SBX 3-roll bending machine, designed for forming metal sheets with a thickness of 4 to 6 millimeters. The machine is specifically engineered to produce cylindrical shells and curved sections with high precision and stability. At the core of the system is the main roller, which is equipped with an electric lifting mechanism. This feature allows the operator to accurately adjust the vertical position of the roller, thereby setting the required bending radius and determining the final diameter of the shell. The electric lift ensures smooth and precise positioning, improving both efficiency and repeatability. In addition, the SBX machine is equipped with independent drives for the lower and upper rollers. This configuration provides better traction and control of the metal sheet during feeding and rolling. By adjusting the rotation speed and pressure of each roller separately, the operator can achieve uniform curvature and minimize deformation errors. Throughout the bending process, the sheet is gradually shaped as it passes between the three rollers, forming a smooth and consistent cylindrical structure. The combination of electric adjustment and independent drives makes the SBX 3-roll machine a reliable solution for bending medium-thickness metal plates in industrial production. The JFY 6 meters by 16 millimeters hydraulic shearing machine is an industrial model widely distributed in Vietnam, typically belonging to the VSO or VR series. It is designed to cut mild steel with a maximum thickness of 16 millimeters and a cutting length of up to 6,000 millimeters. The adjustable cutting angle, ranging from 0.5 degrees to 2.5 degrees, helps reduce material deformation during operation. The machine is equipped with a CNC control system, such as Eston E21S, to manage the back gauge, blade clearance, and cutting time. Its integrated hydraulic system with dual cylinders ensures balanced force, while crossing 12 MOV rectangular blades with 4 cutting edges enhance durability and service life. The video demonstrates the rolling of a pipe section on a 3-roll plate bending machine. The workpiece is made of 1.4301 stainless steel, with a wall thickness of 30 millimeters and a final diameter of 1,355 millimeters. First, the flat plate is positioned between the 3 heavy-duty rollers. The 2 lower rolls support and drive the plate, while the upper roll applies adjustable pressure to initiate bending. As the machine starts, the plate is fed forward and backward through the rolls. Gradually, the upper roll moves downward, increasing the forming force and creating a controlled curvature. Because of the considerable thickness of 30 millimeters, multiple passes are required to achieve the desired radius. The rolling process is carefully monitored to ensure uniform deformation and to prevent surface damage to the stainless steel. Step by step, the plate transforms into a cylindrical pipe shell. The edges are pre-bent to minimize flat sections at the ends. Finally, the shell reaches the required diameter of 1,355 millimeters, forming a precise and round horseshoes, ready for subsequent welding and assembly into a pressure vessel or tank structure. The video introduces the mechanical section bending machine MC150B. A reliable and versatile solution designed for bending various types of steel bars, pipes, and profiles with high precision. Presented by Neressa, this machine demonstrates how to achieve accurate bends through correct roller configuration and proper operating techniques. It is especially suitable for workshops that require flexibility, durability, and consistent bending quality. To bend a flat bar along its flat side, rollers number 3 and number 5 are fully adjusted in position. The washer number 2 and nut number 1 are then installed securely. The operator lowers the top handle until it contacts the material. The machine is moved to the right while lowering the handle gradually, always without applying excessive load or pressing directly on the metal bar. The operator then moves the machine to the left and repeats the process. This alternating movement continues until the required bending radius is achieved. The same rollers are used when bending the bar along its edge. Only the opening between the rollers needs to be adapted to match the material's dimensions. One of the advantages of this machine is the ability to produce multiple identical rings from a single 6-meter bar. After bending the bar into a circular shape, the rings can be cut to size, ensuring uniformity and saving material. For bending square section bars, roller number 4 is placed on the side of the material to be bent. Roller number 5, along with the washer and nut, is then introduced. The square or rectangular bar is fixed in place, and the nut is adjusted manually. The machine is also equipped with side correction rollers that help straighten the profile if necessary, ensuring a precise and uniform curve. Round bars of different diameters can be bent using the same rollers and the same working procedure. When bending square or rectangular tubes, rollers number 5 and number 4 are combined and adjusted to the tube size. The nut must always be tightened by hand, never with a spanner, because during bending the tube expands slightly and excessive tightening could damage the material. The MC150B also allows easy bending of U-profiles both inward and outward. For T-profiles, roller number 5 with the shoulder facing inward and roller number 3 with the round edge inward are placed on the 2 lower axles. The upper rollers are positioned flat, without any gap with rollers 3 and 5. If the profile is angled, the roller assembly remains the same as for a T-profile. The 2 side corrector rollers should always be used to straighten the profile and obtain a high-quality bend. For stainless steel, aluminum, brass, or other delicate materials, Neressa provides special rollers that prevent surface contamination and ensure smooth bending. When bending small tubes, 2 channels can be machined on the same roller to accommodate different diameters. For round metal tubes, hardened steel rollers tempered to 58 Rockwell are available, offering improved durability and bending performance. Each tube size must be carefully matched to its corresponding roller channel to achieve the best result. The manufacturer also produces custom rollers for special profiles and large radii. If space is limited or height is an issue in the workshop, the machine can be tilted to improve operator comfort and accessibility. All machines are manufactured under strict quality control standards and come with a 3-year guarantee. With its robust construction, flexible configuration, and wide range of compatible profiles, the MC150B mechanical steel bending machine is a dependable solution for professional metalworking operations worldwide. Worm wheel gear hobbing is a high-precision machining process used to manufacture worm wheels that mesh accurately with a worm shaft. In this process, a specially designed cutting tool called a hob is selected. The hob has the same profile as the worm that will engage with the finished gear. During operation, the hobbing machine rotates both the hob and the gear blank in perfect synchronization. As the hob gradually plunges into the rotating blank, it continuously removes material to generate the required helical tooth profile. The coordinated motion between the hob rotation and the indexing of the gear blank ensures accurate tooth spacing and geometry. In many cases, the machine table is raised progressively to achieve the full depth of each tooth. This method is widely used for high-volume production because it provides excellent accuracy, smooth surface finish, and consistent quality. However, it requires specialized hobs and a precisely synchronized hobbing machine. In the induction brazing process for manufacturing a finned heatsink, the base plate and aluminum fins are first precisely assembled and aligned to ensure maximum contact. The workpiece is then positioned inside an induction coil supplied with high-frequency, alternating current. This current generates a powerful electromagnetic field which induces eddy currents within the metal components. As a result, heat is produced directly inside the joint area, allowing rapid and uniform temperature rise without direct flame contact. A specially selected filler alloy placed at the joint interface melts when the required brazing temperature is reached. The molten filler metal flows smoothly into the narrow gaps by capillary action, creating strong, continuous, and thermally efficient bonds between the fins and the base. Finally, the assembly is cooled naturally or under controlled conditions, forming a durable heatsink with excellent mechanical strength and high thermal conductivity. The molding sand preparation system is designed to enhance sand quality for mold making in foundries. It involves feeding, screening, grinding, mixing with binders and additives, moistening, and aging the sand to achieve ideal molding properties. This ensures consistency, strength, and workability in casting operations. The steel structure fabrication process in the workshop is carried out in a systematic and precise manner. First, raw steel materials such as H-beams, I-beams, and plates are carefully measured and marked according to technical drawings. Next, the steel components are cut using specialized cutting machines to ensure accurate dimensions. After cutting, workers assemble and weld the parts to form columns, beams, and trusses. Finally, the finished structures are cleaned, inspected, and prepared for painting before delivery to the construction site. The final stage in the production of a welded steel pipe. After all circular and longitudinal seams have been completely welded, the pipe reaches its last processing step. At this point, customized cutouts are made according to each customer's specific requirements. The fully welded pipe is positioned on a rotating frame, which allows precise access to every section of the surface. The required windows have already been pre-burned into the original steel plate before it was formed into a pipe. Now these openings are carefully cut out using autogenous flame cutting. To ensure an ideal and accurate cutting line, a small flame-cutting machine is employed. This device is guided along mounted toothed rails that are firmly fixed to the pipe's surface. The rail system guarantees stability and precision during operation. As a result, the steel pipe is completed with high accuracy, meeting both technical standards and individual customer specifications before delivery. The documents show the construction work carried out on July 8, 2024, to raise the height of the L1 lava defense wall in Svartsengi. The embankment, located near Sillingarfell, stretches toward the Svartsengi geothermal power plant and the famous Blue Lagoon. Depending on the section, the wall is being increased by 4 to 9.5 meters, bringing its total height to between 10 and 21 meters. Shortly before the eruption ended, lava steadily rose along the barrier and successfully overflowed it on June 18, 2024. In response, crews worked urgently to cool the lava and reinforce the structure. Their main objective was to slow the advancing flow, as the power plant was only about 1 kilometer away, making the protection efforts critical and time-sensitive. The manufacturing process at SIAG begins in the outdoor storage yard, where incoming steel plates are prepared for production. Each plate is first pre-blasted to remove scale and impurities, creating a clean surface for further processing. This early surface treatment ensures optimal weld quality and long-term corrosion protection. Every year, up to 100,000 tons of steel are processed, supported by a proven storage strategy and long-term supplier partnerships that guarantee stable material availability and reliable pricing even during fluctuations in the steel market. After preparation, the steel plates are rolled into cylindrical sections according to customer specifications. In SIAG's production facilities across Germany, the Czech Republic, France, Egypt, and the United States, steel tubular tower segments are manufactured, with heights reaching up to 125 meters, diameters of up to 6 meters, and individual weights of as much as 100 tons. Engineering teams develop the most economical tower configurations based on project requirements, ensuring both structural efficiency and cost-effectiveness. The rolled shells are then joined using advanced welding technology. Highly efficient submerged arc welding systems are employed to produce precise longitudinal and circumferential seams. These automated welding machines guarantee consistent penetration, high strength, and dimensional accuracy. Throughout this stage, the Quality Management Department continuously monitors parameters such as weld geometry, material properties, and alignment to ensure compliance with international industrial standards. Once welding is completed, each tower segment undergoes comprehensive inspection procedures. Non-destructive testing methods verify structural integrity, while dimensional checks confirm adherence to design tolerances. All production sites operate under certified quality management systems that supervise every step of the process, from raw material inspection to final documentation. Following inspection, the segments move to large blasting and painting cabins capable of accommodating tower sections up to 35 meters in length. Here, surfaces are thoroughly blasted again to achieve the required cleanliness grade. Protective coating systems are then applied according to customer specifications. Special attention is given to coating thickness and uniformity to guarantee durability and long service life under harsh environmental conditions, including offshore and high wind regions. The towers are subsequently equipped with internal and external components. Technicians install ladders, platforms, stair systems, cable routes, railings, and other galvanized steel structures. Optional special equipment, such as service lifts and conductor rails, can also be integrated. This pre-assembly reduces installation time at the wind farm site and ensures that each tower segment is delivered as a nearly complete unit. Before shipment, every tower undergoes a strict final inspection and receives full quality documentation. Loading operations are performed using overhead crane systems or mobile heavy-duty cranes, depending on size and logistics requirements. The finished components are then transported worldwide, delivered directly to the construction sites where they are erected shortly after arrival. In parallel with tower production, SIAG manufactures generator frames and machine carriers. These large welded steel constructions can reach lengths of 12 meters, widths of 6 meters, and individual weights of up to 60 tons. The production process includes forming, machining, and plasma welding, all carried out with high precision. Each unit is blasted and coated according to customer requirements and can be delivered fully equipped with aluminum walkways, cable supports, oil trays, and grease pans. With an annual capacity of approximately 450 units and up to 2 generator or machine carriers leaving the Czech facilities per day, the company demonstrates a high level of productivity and flexibility. Small components are produced in-house and pre-assembled as required. Once delivered to the wind farm, SIAG towers are erected immediately, enabling wind turbines to be installed and brought into operation efficiently and reliably. The video shows the loading process of 20-meter-long tank roofs. Each bundled section weighs approximately 18 tons, requiring careful handling and precise coordination. To transport these oversized components, the trusted logistics partner Lens arrived with a heavy-duty semi-trailer designed for exceptional loads. The operation demanded extensive know-how, strong concentration, skilled workers, and a highly durable overhead crane. Later, these large segments will be welded together to form a complete circular tank roof used for storing diesel, gas, mineral oils, or even sugar beet syrup. The video shows the bending process of an 80mm thick S355 sheet metal using a heavy-duty press brake. The bending length is 2,500 millimeters. First, the large metal sheet is carefully positioned on the lower die. Due to its thickness, a powerful hydraulic press is required to apply sufficient force. As the ram descends, the punch gradually presses the sheet into the die, creating a precise bend along the desired line. Throughout the operation, slow and controlled movement ensures accuracy and prevents damage. After bending, the ram retracts, revealing a clean, consistent bend angle. The process demonstrates the machine's capacity to handle high-strength, thick materials with precision in heavy metal fabrication.